Okay, so we'll start now. Good morning, all of you, and welcome to the last of this parallel sessions today in the ASI 2022 meeting. So this is the fifth session, around 10 minutes. Your talk duration is 12 minutes plus 3 minutes for any question, answer, or discussion. So Meera, you may please start your presentation now.
Okay, thank you for the introduction. So I'm Meera Nandakumar. I'm a PhD student from IIT BHU Varanasi. So this work is being in collaboration with Prasun Dhang and Thomas Jarrett. The title of my talk is Understanding the Interstellar Turbulence and its Implications in External Spiral Galaxy NGC 5236. The interstellar medium, or in short ISM, is the medium that present in between the stars in the galaxy, and the dominant part of the ISM is atomic hydrogen atom, or in short H1. So here is the optical image. What you see in the background is the optical image of the NGC 5236 galaxy obtained from DSS survey. And this white contours represent the H1 column density H1 profile of the NGC 5236 galaxy from THINK survey. So it is a well-known thing that is found to have turbulent dynamics because of the presence of random density and velocity fluctuations. ISM turbulence plays several roles in the different activities in the galaxy. For example, it plays a dual role in the star formation activity, like it sometimes it triggers the star formations and sometimes it can hindrance the star formation too. So people have found the existence of unstable phase in the ISM in between the cold neutral medium and warm neutral medium. And there are hints that turbulence is the fueling factor for the continuous generation of this unstable phase. So even though we know all of this, there are still some questions unanswered, like what is the source of the turbulence, what is its energy input, at what scale it is injected, etc. So in this work, we are motivated by this question to do this work, where we would like to do the statistical measurement of ISM turbulence and understand its influences. So it is observed from several studies that the ISM have density fluctuations, which and these density fluctuations found to have coherent structures that exist from the scales of galaxies to the scales of giant molecular clouds. And these density fluctuations or the velocity fluctuations can be probed by a tool, power spectrum. So power spectrum is a 2-point statistical quantity, and the power spectrum of the turbulent generated fluctuations are expected to obey a power law. Datta and Nandakumar 2019 has done a comparative study between the several power spectrums that are available in the literatures, and they found out that power spectrum from directly measured visibilities are reliable, where visibilities is the quantity that a radio interferometer measures during the observation. So their comparative studies results are basically depicted in this plot. So this is not the first work. This is not the first study on the density and the velocity power spectrum. So there are several studies of densities and velocity power spectrum at KPCs at parsecond scales in our galaxy Milky Way. And recently, Datta et al. 2013 has estimated the column density power spectrum of around 18 spiral galaxy, and they found that all of them is obeying a nice power law, which is indicating the presence of turbulence there. They also found that the power spectrum of dwarf galaxy is also obeying power law. So by the estimation of column density power spectrum, we can indicate the turbulence dynamics. But to really understand the source behind the turbulence, we need line of sight velocity power spectra. So finding out, there are several estimators which do the velocity power spectrum estimations in our galaxy, but estimating the power spectrum of velocity in external galaxies is rather difficult. And Datta 2016 has introduced a method to find the H1 velocity power spectra using the visibility moments. And based on that, we implemented a new estimator, visibility moment power spectrum estimator, in short VME, which does the power spectrum estimation for H1 density and velocity. And our first sample for the implementation was NGC 5236 or Misra 83. It is a nice barred spiral galaxy, which is almost nearly a face-on galaxy. And we freshly observed the 1 centimeter observation of this galaxy with UGMRT with better resolutions, and be able to estimate the column density power spectrum from that observation. So this plot basically represents the results of that estimations. So here the white open circles are representing the power spectrum, column density power spectrum obtained from UGMRT observations, and the black circles are representing the previously estimated power spectrum from things data. So we combine these two data to obtain a better power spectrum. So the final combined power spectrum is what given with error bars. So we can clearly see a nice power law is following here, which is indicating the presence of turbulence cascade that ranging from 11 kpc to 300 parsec, which is almost around 2 decades of length scale. And the slope of the power spectrum is around minus 1.23, which is consistent with the previous results. So by doing this estimation, we were able to probe the column density power spectrum to an extra 1 more decade of length scale comparing to the previous results. And we, using the visibility moment estimator, we able to measure H1 velocity power spectrum also. And to the best of our knowledge, this is the first ever measurement of H1 velocity power spectrum in any of the external spiral galaxy. Not surprisingly, here also it is obeying a nice power law, as you see in this plot, which ranging from around 6 kpc to 300 parsec. So there are several simulations to see what values of slopes you can get for the density and velocity power spectrum for different cases of compressible turbulence, like different types of forcings like solenoidal, compressive forcings, etc. So those slopes values are given in this table. So these are the slopes values that we obtain. So comparing the results from comparing our results from these simulation results, we able to conclude that the forcing behind the turbulence that we measured here is compressive in nature. So the possible origin for this measured turbulence is either self-gravity or the gravitational instability. So by this, we able to successfully measure the large scale turbulence in galaxy 5236. Now the next question is, what is its implications? So first, we are interested into see its influence in star formation activity. So here is the basic H1 instability equation. So which is a well-known thing. And so when there is a competition happens between these three terms, rotation, gravity, and pressure, and when that gravity wins in that competition, collapse happens, and that is the condition omega square less than 1, basically tells you. So people have studied the connection between H1 instability and star formations from the perspective of entire galaxy. So here, like they take a lot of samples of galaxy and investigate the connections. But here we are interested to find how star formations are connected with other things in the particular galaxy at different length scale. So we use the modified Tumbre criteria for the two fluid disk model. So this is the Tumbre criteria parameter, which is defined in this way. So the condition for the collapse is Qt less than 1. So here we have include the effect of turbulence also. So I am not discussing the analysis in detail because of the time constraint. Yeah. So we need both gas component and star component. So the star mass maps were obtained from Y. So see, this were obtained from our collaborator Tom H. Jarrett. And the gas part, both atomic hydrogen and molecular hydrogen data were obtained from the archivals. Yeah. So using these data, we able to generate the Qt maps of the galaxy at different length scale or at different resolution scales. So these are the QT maps generated at different length scale ranging from 300 parsec to around 4 kpc. So the black contour line represents QT value equal to 1 and white contour represents QT value 0.6. So what this means, whatever the contour regions, what you are seeing is essentially unstable regions. So happily we could able to detect unstable regions in most of the length scales, and most of the unstable regions are following the spiral structures where the star formation activity is large. Now the question is how these unstable regions are correlated with the gas fractions, or how it is correlated with the H1 present there. So to do that, what we does is, for a particular length scale, we try to plot the correlation plot between the QT and the H1 surface density. So in this density map, what you see in the background is the surface density of the H1, and the contours represent the QT values. So we can clearly see that the small values of QT, so this QT values are small values less than 2. The contours represent the QT values less than 2. So these values, so the smaller QT values are highly correlated with the high densities in the H1, which is so that strong anti-correlation between the QT and the H1 is nicely seen in this correlation plot also. The Spearman correlation coefficient is around -0.8. So we try to see how this correlation coefficient will be at different length scales. So we did this analysis for all these length scales, and the Spearman correlation coefficient plots are given over here as a function of length scale. So we can clearly see that the QT values and the H1 mass are strongly anti-correlated at a larger length scale, which means that the possibility of finding high density H1 in unstable regions is large. So we did this similar analysis by taking different combinations of pairs to see what is happening actually. So we tried to find out the correlation between QT and H1 gas, then QT and H2, then between QT and star formation rate, star mass, star maps, then between the we find the correlation between QT and this H1 velocity dispersion, which is kind of an indication for turbulence. So these different plots are basically representing the results for the different correlations. So how the correlation coefficients are varying at different scales. So the overall conclusions that we can draw from this graph is this.
Meera, you have 2 more minutes.
Yeah. So the overall conclusion of this plots are basically in this way, that wherever unstable, so the unstable regions are highly correlated with high density of H1, H2, and H1 velocity dispersion. That means it is saying that possibility of seeing H1 mass regions and a high H1 velocity regions in the unstable regions are high. So basically this is indicating that turbulence is playing a significant role in inducing instabilities. So this was one of our aim in this work. So this work is currently in the process. So this is just the preliminary results of the analysis. So in near future, this work will be presented in a coherent manner. So by this, I will end my talk, leaving the summary slide to you. Thank you.
Thank you, Meera. We have time for a few quick questions. If there are any questions in the lecture hall.
Yes, sir. Yes, ma'am, there is a question.
Yeah, please go ahead.
Meera, sorry, the Kolmogorov spectra that you drew, I saw at various places it was deviating from the Kolmogorov power law index. Could you just throw a light on why it's happening and what do you think why it's happening?
Okay. I didn't understand your question completely. Did you mean this?
No. Go back. Yeah. This one. Yeah. So I think. Yes.
Or this one?
No. It appears that just go back one more.
Yeah.
Not back. So yeah, this one. So you see at higher k lambda, you sort of there is a jump and then it comes down, right?
This.
Yeah. So it is deviating. I don't know what is the power law you got. It is -5/3. That is Kolmogorov power law.
What I got is -1.91.
Okay. That
is the slope of the law.
Okay.
Slope of the pulse spectrum. So this is like compressible turbulence.
Okay, so it's deviating from the Kolmogorov -5/3, right?
Yeah.
Why is it that? I mean, do you have any explanation for that, or any speculation for that?
As far as I understand, the Kolmogorov is for incompressible turbulence. I'm not sure. So, I mean, what I meant is, I think I think Kolmogorov is for incompressible turbulence, I guess. But what we are looking at is the compressible turbulence. What can be the reason? I'm not sure.
Hello, ma'am. There is no question from offline audience.
Okay, so are there any questions from the online participants here? You can also type your questions in the chat box in Zoom and also make use of the Slack channel to continue your discussions further. So if there are no other questions, let us thank Meera for this talk. Meera, if you can please unshare your slide. The next speaker in this session is Prasun Dhang, and he will be speaking about generation and transport of large-scale magnetic fields and accretion flows. So Prasun, I will give you a warning at 10 minutes. Okay?
Sure, ma'am. Great. So let's start. Hello.
Yeah, please start.
Lapel.
Follow mic.
Okay, can you see? Morning, everyone. I am Prasun. I am a postdoc at IUCA, and in this talk, actually, I will talk about something on origin of large-scale magnetic field in accretion flows. So it's a kind of huge topic, so I will quickly go through it. So if you have any question, please feel free to interact in chat Slack. So why are we basically studying it? That I'll talk later. So there will be two parts of my talk. In the first part, I will talk about the generation of large-scale magnetic field, and in the second part, I will talk about the transport of external magnetic flux in the accretion flows. So basically, why are we studying it? The reason is some observations and theories. Let's first look at the first picture, which is a famous Q diagram for black hole binaries. So jets are actually present in the hot state of this sources, these transient sources, and it is thought that there's a hot accretion flow exists close to the center of the crater in this hot state. Also, if you are probably have seen this second image, which is a polarized image of M87 black hole, which is also a jetted AGN. And recent observation shows that there's a presence of a large-scale magnetic field close to the black hole. And different theories, also numerical simulations, infers that we need a large-scale magnetic field in order to produce jets. So if I summarize all this observation and theories, the crux is that we need a hot accretion flow close to the black hole, and it should be saturated with large-scale magnetic flux. This is the requirement for jets, and this has been realized in numerical simulations, and the model is called magnetically arrested disk. But the question would be, what is the source of large-scale magnetic field? Now, the first case is that, okay, the large-scale magnetic field is generated in the disk itself or in the RAF itself by a MRI-driven dynamo, which is responsible for the angular momentum transport. Now, before going into the results, let's look at this equation called mean field evolution equation. The first term in the first equation is basically is responsible for the generation of toroidal field from the colloidal field, and this is something called famous omega effect. Second term, which involves a term called mean EMF, which arises because of the correlation between the fluctuating velocity and magnetic field, is responsible for the generation of colloidal field out of the toroidal field, and this is something known as the alpha effect. And if I want to understand what is alpha effect, think about a toroidal field embedded in a stratified medium, and due to buoyancy, when it is rising up, if there is some kind of twisting motion, let's say some kind of helicity, then it can generate colloidal loops out of the toroidal fields. So this is kind of the picture what people think about alpha omega dynamo. And we want to understand whether this kind of dynamo can generate sufficient amount of large-scale magnetic field in RAF. So the first thing people do to look at the dynamo is to look at the butterfly diagram, and this is nothing but the spatio-temporal variation of the mean toroidal field, and the y-axis is the latitude. So if you are looking at the midplane, is basically disk midplane, and x-axis is the time, and we are looking at a particular radius. Here we have chosen as the radius as the 20 Schwarzschild radius, sorry, gravitational radius. Now you can see the mean toroidal field flips intermittently or irregularly. If you compare it with the same butterfly diagram of a thin disk, it's pretty regular. So the reason behind this intermittency is the slightly subcapillary nature of the angular velocity in the RAF, and this is a generic feature of a thick disk. Next, we look at the helicity distribution as a function of latitude. So as you can see in the midplane, and that means at smaller latitudes, the helicities are vanishing, while as you go up or down, that means you are going at higher latitudes, the helicities become non-vanishing, and indicates that in the midplane, basically magnetic fields are grown by the random stretching of the magnetic field lines, and this is basically fluctuation dynamo or small-scale dynamo. While at larger scale heights or larger latitude, a helicity-driven large-scale dynamo operates and dominates the process. Now, we also basically quantified the different dynamo coefficients as I have shown in the first equations. Out of the many coefficients, I will only talk about the two which are of particular importance. The first one is alpha phi or alpha effect, which is responsible for the generation of colloidal field out of the toroidal field. And here I have shown you the colloidal distribution of the alpha phi in the left panel. And as you can see that at larger latitudes, those are actually showing a sign change, while in the midplane there's a black mask. The reason is that in the midplane, small scale dynamo dominates and results are not reliable. So this is kind of fine. But also we found that alpha effect is weak. Next one is the turbulent, something called turbulent pumping, gamma R, which is responsible for the generation of, transport of large scale magnetic field from the laminar region to the turbulent region. And here gamma R is positive. That means basically it is prohibiting to gather the magnetic field close to the black hole. So if I combine both weak alpha effect and strong turbulent pumping, then it says that basically in RAF, it is difficult for a dynamo to produce sufficient large scale magnetic field close to the black hole, which can produce jets. But there can be another source, something called advection of external magnetic flux from some external sources. Now, for example, in X-ray binaries, it can be the companion star. In low luminous AGNs, it can be the accreting magnetic ambient medium, which also harbor the magnetic fields. Now, actual configuration of the magnetic field could be quite complex. But as a first step, we did the controlled experiment of advection of magnetic field loops in a fully turbulent drive. So this is the very different from the earlier studies where people have injected the magnetic field in the laminar stage and they have considered it. So to the best of my knowledge, this is the first study which injected the loops in a fully turbulent drive. So first attempt would be, we have to construct a fully turbulent drive and which will forget the initial condition. So what we have done, we have considered with initial colloidal field loops and we run it for long enough so that it forgets the initial condition. So, by the way, this is a GRMHD simulations using Ethernet++ code. So let's see how it rolls. So right hand panel shows here the mean B5 and left hand side shows the mean BR and streamlines are basically the colloidal field lines. So as you can see that MRI basically dominates at the late stages and everything becomes turbulent. So there is no signature of the initial field geometry. So the movie is quite long, but due to the time constraint, probably I'll skip it. Yeah. So we want to inject the field lines or magnetic field loops in the quasi-stationary state. So we have to calculate during the runtime how much of the region is in a quasi-stationary state. This has been defined by something called inflow equilibrium radius. So to do the diagnosis, what we looked at the radial profiles of mass accretion rate at different times. So blue line is the latest time of the simulation, and wherever the region is flat, we call it an inflow equilibrium radius. So for the blue line, you can see roughly the inflow equilibrium radius could be around 60. Next, I also, as I have told, I want to inject the field lines in the weakly magnetized diaph. So I want to see something whether it has reached MAD or not. And to quantify it, to look at something called MAD parameter or phi gauge, which is basically the radial flux threading the event horizon of the black hole and normalized with the square root of mass accretion rate. And if it is above a critical value, let's say 40, then we call it a MAD. Now in our simulation, you can see in the bottom right that throughout the simulation it is always driven below 2, so which is a kind of supersend regime. There is no MAD at all at any time of the simulation. Now in this stage, we want to inject the different magnetic field loops of different strength, as shown by the top 6 panels, different vertical size and different radial size. Also, we look at the effect of injection location, as shown by the last 2 panels. Now let's see how it happens if I inject the external magnetic field loops in the turbulent drive. So you can probably see in the left-hand panel the loops pretty clear. I think it is clear. Let's see. And we have injected the loop in between 60 and 90 gravitational radius of plasma beta 1500, which is kind of moderate. And let's see how the loop does. So it is slowly drifting towards the black hole, and as you can see, that it is enhancing the magnitude of the magnetic flux close to the poles. And if I compare it with the original RIAF run without injecting the flux, you can see the difference. So some of the flux is really reaching the black hole, but slowly. Now let's consider a very strong flux. So beta small means strong flux. So here you can see this just quickly plunges through the black hole, and this is probably expected because it generates the large scale stresses which transforms the material as well as the magnetic field very quickly. Now, different magnetic fields loops will harbor different amount of magnetic flux, but we are particularly interested in the efficiency. That means we want to look at how efficient the transport process is. So we looked at different things like plasma beta, which will define the magnetic field strength, vertical size, radial size, and also injection location. We consider the off-centered loops. We found that around 15 to 14% of the loop, like magnetic field loops, are being transported to the black hole. Rest of them will be diffused or reconnected. And we also find that size doesn't really matter in this case, at least the parameter space we have scanned for, either vertical size or radial size. Interesting thing we found that off-centered loops are show poor efficiency of. The reason behind that, for the off-centered loops, due to the shear, both like the toroidal field will be converted quickly to the toroidal field in a dynamical time. And
Soon, you have 2 more minutes left.
Yes, this is my last slide. So it will create the toroidal fields of alternate polarity in the same hemisphere, and they will quickly reconnect and diffuse. So they cannot really reach the black hole. So we have also looked at some hand-waving calculation to look at the minimum toroidal field required at the injection location in order to reach the map. So this is the formula we come up with. And we found that if we inject the magnetic field loops around 100 gravitational radius for a 10 solar mass black hole, which is typical mass for the X-ray binaries, then kilogauss field is fine. That will eventually create the band. Although we are silent about one feature is the coherence of the field. That is also required. So here is the summary of my talk. So we found that dynamo is probably not efficient enough in the dryad itself to generate the strong enough colloidal flux in order to produce jets. If we talk about the external magnetic flux, a certain fraction of the external magnetic flux is reaching the black hole, which is I would say a moderate amount. And we found that in the parameter space we have scanned for the vertical or the size of the flux, it doesn't really matter. And we've also found that off-centered loops are basically show very poor efficiency in transporting the magnetic field. And the final conclusion would be probably mag will be easier to form, provided there is some that our experiment we have done in the parameter space we have scanned is maintained in the nature. Yeah, that's all I want to say.
Thank you, Prasun. Questions from the people present in the lecture room?
Prasun, good talk. Did you check, I mean, sort of estimated the resistivity, although I know it's an ideal image. Because you see, physically speaking, the magnetic field cannot enter the black hole.
Yes.
Okay. So therefore, what can it do physically? It can generate, because the region is very compact near the black hole, it should generate a lot of resistivity.
Yes.
Okay. So if you can you sort of measure, I mean, posteriorly, after the simulation is done, and instead of plotting the plasma features and all, it is better if you can measure the resistivity. Then there will be an indication that the magnetic field is actually decaying near the horizon.
Yeah, so that's a good question. The reason is that we have not done it for GRMHD, but we have done it for our earlier case in MHD simulations. The problem is that we have to do control volume analysis of the whole domain, which is kind of very expensive even in post-processing. And people have found that the resolution we have used, the effective Reynolds number would be around 5,000, which is probably one of the highest achieved in global simulations of accretion flows. And here all the resistivities comes from the grids, as we are not putting any explicit resistivity. But there is another thing, something called turbulent resistivity as well, which is much more dominant over the explicit resistivity. So we have computed it in shearing box simulations, and which we found order of magnitude larger than the grid resistivity. So I think we are fine, or we think as a community we are fine. But again, as we increase the resolution, ideally we should reach around 10 to the power 18, 10 to the power 17 Reynolds number, which is I think kind of infeasible unless something big comes up.
Any other questions from the auditorium?
No, ma'am, there is no question from offline.
Okay. So Bhargav has a question from the Zoom participants. Bhargav, you may go ahead.
Thank you, Kuntal. Prasun, can you hear me well?
Yeah, I can hear you, Bhargav.
Yeah, Prasun, you mentioned about the acting of MRI in order to transport the matter in your readouts. So usually in GRMHD simulations, people actually compute something called as the quality factor.
Yes. Yes.
So have you estimated that, and whether that estimate remains MRI unstable throughout your simulation?
Yes. So for generally it is told that empirically, if the two quality factors, the multiplication of Q theta and Q phi, if their multiplication is above 200, we say that okay, it is resolved. So for our simulation is around 250 throughout the runtime. And also, I think the better quality factor would be the magnetic tilt angle. And people have found that it is above 10 degree, then simulation is well converged. And for our GRMHD simulation, we found it to be around 13 degree. And for our MHD simulation, it was much more better, around 14 degree.
Okay, and this was also true when you included the magnetic flux. When you injected the magnetic flux, the quality factor remained the same.
It will increase because we are adding the magnetic flux on top of the existing field. So it will enhance the quality factor.
Okay, fine, thanks.
Any other questions from the online participants?
Offline, I have one.
Okay, go ahead.
So when you say that there is a need of like high magnetic quantum flux, so how high is you will call it high, because like as the observation.
Yes, sir. This is the MAT parameter people looked at.
Yeah, because like observationally, like as the observation are being more refined. So initially, like for MIT7, it was supposed to be like somewhere around 160, 180. Then now number keeps on coming down based on this like recent this polarization image suggests that it should be somewhere around 30 or 40 some.
Gauss, even Gauss.
30 Gauss. Yes.
30 Gauss. See, this is a dimensionless number. So it is normalized with the mass accretion rate. So it should not change. So that is it is irrespective of the mass of the black hole. Because essentially for AGS, the mass accretion rate will be low, while for X-ray binaries it will be high. Oh, sorry. Ulta.
Yeah, but there shouldn't there be an interplay between this magnetic energy density and thermal energy density? So which dominates? Like let's say the matter is too hot, then it doesn't care about magnetic field at all.
It depends on the process you are looking at. If you are looking at Blandford-Snack, probably quantum flux will dominate over the radiation. But so far, I think more consensus is from numerical experiment is that Blandford-Snack probably dominates over all other processes. At least we have found. But again, Christian Friend is working on something where they found Blandford-Wayne also works.
Yeah, so like the Blandford-Wayne, like from the initial, it is that it is like the accretion rate is too low, like not a great field like vacuum, but.
No, it's not vacuum. It's the magnetic field is embedded in the disk
itself, but the mass accretion rate is low initially.
In
Brajesh mechanism, like you don't have like very high accretion rate.
See, as I have heard from people who are doing jet simulations, as long as you have a strong magnetic colloidal flux, nothing can kill the jet.
No, a lot of matters will kill. Okay, if you can generate a lot of electric field, it will kill. That's our Andrew Fabian and Hill's paper. They are saying that it will generate electric field anyway. Okay. So that apart, if you have a lot of matter, Blandford-Snack is not supposed to, because if you look at Blandford-Snack's original paper, okay, it is basically vacuum.
Yes,
right?
I agree. Yeah.
Okay, and then you give a little bit of particles, that is pairs, just to kickstart the thing.
Oh, by the way, when I'm saying the matter, I'm talking about the disk, not the funnels. Funnels are generally almost vacuum. Like if you compare the density of disk and funnel, it is order of magnitude less. For example, here if it is 10 to the power 6, let's say, it will be 1 here. So we always find a vacuum along the poles. So that is the reason.
Okay, thank you, Prasun.
Yeah. Thank you.
We'll move on to the next talk now. The next talk is by Rajdeep Agrawal, who will be speaking about search for Lorentz Invariance Violation from stacked gamma ray burst spectral lag data. So Rajdeep, I guess you're giving the talk online. So please share your screen.
Yeah, thank you. So can I start?
Oh, yeah, please start.
Yeah. So good afternoon, everyone. My name is Rajdeep Agrawal, and I'm a final year undergraduate student at IIT Hyderabad in the Department of Physics. So the topic for of our research and presentation today is the search for Lorentz Invariance Violation using the stacked spectral lag data of gamma ray bursts. So brief introduction, as most of us might know, gamma ray bursts are extremely energetic and some of the brightest and most luminous known events to occur in the universe. And in recent times, gamma ray bursts have formed a very useful, proved to be a very useful probe for Lorentz invariance violation due to the energies and redshifts at which they're detected. So typically the quantum gravity energy scale at which these gamma ray bursts are detected are almost close to the Planck energy scale at which LIV is supposed to set in. And the spectral lag data that we have used for analyzing these gamma ray bursts is essentially the time lag data between the arrival of the low energy and high energy photons of these gamma ray bursts, since one of the major consequences of LIV is that the velocities of photons will now be a function of their energies in vacuum and no longer constant as the speed of light. So a small summary of the data sets that we have used for our analysis. First, we had the Wei et al. Data of GRB 160625b, which comprised of 3 isolated subbursts. And from the second subburst, we were able to extract, they were able to extract 37 independent spectral lag measurements, all at a common redshift of 1.41. And this was one early research where they had claimed that sufficient evidence for spectral lag overturning, that is LIV observation, was present, but that was later almost refuted in with further statistical analysis in another 2017 paper. The second data set is Ellis et al., who took a slightly more diverse number of GRBs in a redshift range as specified here. And the upper energy band of these GRBs was around 115 to 320 keV, and a lower energy band of 25 to 55 keV. And the final data set, a slightly peculiar one, this one was from the Du et al. Paper, again comprising of a single gamma ray burst of a constant redshift of 0.4245. And in their paper, they use opposite sign for the intrinsic parameters, intrinsic lag parameters, which we will incorporate in our research as well. And the higher energy band, if you see, has a very higher upper limit, which is around 5000 keV, which is quite high as compared to the other data sets that we have used. This was the result of a preliminary analysis on only the Wei et al. Dataset, where we fit the 3 model hypothesis functions, which is the null hypothesis, which includes only the intrinsic time lag, and the n equal to 1 and 2, which is the linear and quadratic LIV models, were fit on the spectral lag data provided in that paper. And as we can see, for higher energies of observation of these gamma ray bursts, we observed that the LIV based models show that tail towards the end, which proves to be a better fit on these higher energy scales, whereas the null hypothesis almost diverges from those points. So a brief the thing about the mathematical modeling of these time lag equations. So the total observed lag of between the low energy and high energy photons of gamma ray bursts is taken to be a combination of the intrinsic astrophysical emission lag and the LIV induced lag. So the intrinsic lag is calculated in the observer frame by multiplying with the cosmological redshift to the original source frame time lag. And this intrinsic lag itself has 2 unknown parameters, which have to be optimized, tau and alpha, along with E naught, which we assume to be the median of the lower energy bin of the gamma ray bursts, and E is the observed energy at which the emission was observed. And so the second term which we have is the LIV induced time lag, which is part of the n equal to 1 and 2 models. So this comprises of, so that is what the n represents here. And we have H naught, which is the Hubble's parameter. And in the integral, if you see, we have a term H of Z prime, which is the redshift dependent Hubble's parameter, the reduced quantity. And that in a cosmological model dependent sense, it would depend upon the redshift in a basic formula that we are aware of. But since we're dealing with energies close to the Planck scale, where the cosmological model may not be applicable anymore, so we have tried to reconstruct this Hubble's constant as a function, as a non-parametric function of the redshift using Gaussian process in Python, thereby eliminating the dependency on the standard lambda CDM model. And we also had the energies, the errors observed in the observed energy, as well as the time lag, which was present in the spectral lag data. So these are the results. This is the prior transform ranges that we had used for our nested sampler in Python to compute the best fit parameters and the Bayesian evidence for the different models. So we have, since the last data set, Du et al., they had negative signs on, they had opposite signs on the intrinsic lag parameters. We had to expand the scope of the prior transform ranges for the tau and alpha, which are the intrinsic parameters, in order to incorporate that. And the best fit values obtained from the sampler are listed here. So in cases where we see an empty cell, it's because the close bounds on those values were not obtained from the sampler. And if we observe again for the LIV energy values, the EQG, we see that it's close to 10 power 16 or 10 power 7 in this case, which kind of approaches for high energy gamma ray bursts. It actually approaches the Planck's energy scale of 10 power 19 GeV in some cases. And in the table below, we see the parameters to estimate the goodness of fit and a model comparison. So the reduced chi-square is empirically supposed to be close to 1 to indicate good fit of the model. So in this case, it's close to 10 or 11 in almost all the cases, which does not signify a very good fit. And the base factor for the LIV models, if we see, is almost very negligible for the linear model, which almost gives no evidence in its favor, whereas the quadratic model with LIV of 25 still has a strong evidence in its favor, though it is not decisive enough to overturn the null hypothesis. Because so this was the analysis done with common intrinsic lag parameters tau and alpha throughout the entire stacked set of gamma ray bursts that we had. But because the final data set in our analysis uses basically has gamma ray bursts spanning over larger orders of magnitude, as well as detected over a much higher upper energy band, along with opposite signs for the intrinsic parameters, it was considered prudent to try and analyze that data set with separate intrinsic parameters tau and alpha. So to that end, we have chosen distinct, GRB dependent intrinsic parameters for the analysis and perform the same operations again. So again, from the sampler, we obtain the best fit values for the different intrinsic for the different parameters. Again, places where it is empty is because we could not get a closed bound on those parameters from the sampler. And again, if you observe the LIV based energies for the linear and quadratic models, again approach like 10 power 14 or 10 power 6. So again, kind of moving towards the Planck scale of 10 power 19 GeV. And for the goodness of fit of the models, we see that the reduced chi-square value is much higher for the intrinsic model as compared to the LIV models, indicating that the LIV models are a slightly better fit. And even comparing with the previous analysis, the reduced chi-square for the LIV models is between 4 to 7, which is lower than the previous values of 10 to 11 almost. And the major difference here is in the base factor, which was quite insignificant previously. It is now almost it's overwhelmingly large in this case, thereby presenting substantial evidence in favor of LIV with this analysis of GRB dependent intrinsic parameters. So the final conclusions of our of this research is by performing 2 independent analysis on stacked gamma ray burst data from 3 sources. We have first modeled them with common intrinsic parameters, in which the quadratic LIV model gave us some strong evidence for LIV, but it wasn't substantial enough. And then when we used the GRB dependent intrinsic parameters to single out the last set of GRBs, then we got substantial evidence in favor of the in favor of both the LIV models that we had used. And the analysis performed was absolutely identical in both the cases. So that's it about the presentation, and just a note of thanks to my supervisor Shantanu Desai sir, who is also part of this conference, and this research was done in collaboration with him. And yeah, these are the references. And this is just the appendix about various model comparison techniques, the Bayesian model comparison and estimation of chi-square from the log likelihood. These are the Bayesian credible regions, again obtained from the sampler. These are for the common intrinsic parameter case for the 3 different models, the LIV independent model, the linear LIV model, and the quadratic model. And these are the same regions for the case with GRP dependent intrinsic parameters. As you can see, we have a different intrinsic parameters here. So again, for the 3 different models. So yeah, that's the end. Thank you.
Thank you, Rajdeep. Any questions from the audience?
No, ma'am, there is no question from offline audience.
Okay. From online participants, is there any question? Okay, Rajdeep, I have one question.
Yeah.
So here you showed the case of 1901-14C. I may have missed this point in your talk, but did you also, how many other GRBs did you try this with?
We have 3 independent papers from where we collated the GRB sources. So in the second paper, we had a whole lot of GRBs. The 190114C was one of the GRBs taken from the third paper. So we have like a whole lot of different GRBs.
Okay, and what was the selection criteria for choosing only those GRBs on which you run this analysis?
That was primarily based on like the recent research which was done on similar kind of GRBs. So whatever was suitable to what we wanted to do, our aim was to basically develop some sort of unified model where we can stack these gamma rivers and check if there is some evidence of LIV. So whatever individual works were done in this regard, that is what we stacked eventually.
And this comprises of both long and short bursts. You
Yes.
have not made any distinction between them.
Yeah, we have not stated that explicitly here.
Okay, thank you. Okay, if there are no other questions, let us thank Rajdeep for this nice talk. The next talk is by Sayan Kundu, and he'll be speaking about numerical modeling and physical interplay of stochastic turbulent acceleration. So Sayan, you may please go ahead and share your screen.
Am I audible? Hello, am I audible?
Yes, you're audible. I'll give you a warning at around 10 minutes. Okay, so you can start your presentation now.
Hello everyone, I am Sayan, and the subject of my presentation today is numerical modeling and physical interplay of stochastic turbulent acceleration. I'll be focusing on a single astrophysical object, namely the radio lobe of FR2 and this work has been done in collaboration with Dr. Bhargav Vaidya, who is my PhD supervisor, and Dr. Andrea Mignone. So first, let me tell you why stochastic acceleration is important. There are observations which indicate turbulent acceleration as a candidate to explain certain observational feature. Likewise, in the left panel, we can see a radio galaxy in two different frequencies. An interesting observation is that the size of the radio galaxy does not shrink with increase in frequency as it should be because of various radiative losses. That implies the presence of some distributed acceleration in energies to energize this particle so that they can radiate even in higher frequency. Another plot here in the right-hand side shows a diffuse emission around the hotspot region of radio galaxy, which also requires a distributed mechanism present around the shock region to induce the diffusion in the emission. Also, there are certain observations which says that the Aegean jets are found to have a X-ray kind of halo around it. Here in the left panel, we show a plot of Centaurus A, which is a FR1 radio galaxy, where you can see the blue line depicts a radio emission. This radio some sort of distributed emission, some sort of distributed acceleration process has been attributed to indicate this radio emission in FR1 galaxies. Similarly, in FR2 galaxy, as I have shown here in the right hand side, we can see a FR2 galaxy which is submerged in radio kind of halo shown in blue. Moreover, observations suggest that in radio lobes, spectral index maintains a constant kind of value. Here, we show such radio lobe where one can observe a constant spectral index kind of structure as we move along this white line. In the top panel, we show, or it's been shown, the flux with this distance when one traverses to this white line. Being said that, let me tell you how this stochastic acceleration works. Stochastic acceleration is a process where non-thermal particles get energized by random interaction with imaging waves and magnetic inhomogeneities. Particles can both energizes and de-energizes by this process, and that is the origin of stochasticity in the stochastic acceleration process. This process is usually numerically modeled with a Fokker-Planck equation where this diffusion coefficient takes care of the random energization. There is another acceleration process which is known as shock acceleration, where the particle gets energized by crisscrossing the shock. The numerical implementation of the numerical modeling can be done of this acceleration process by this way, where one convolves the upstream spectra with a suitable kernel to the downstream spectrum. The shock acceleration has already been implemented in the code Pluto, which we use for our simulation, and with various radiative losses. We extend the already implemented module by incorporating the stochastic acceleration. We have used a second order accurate RK-IMAX SSP algorithm, which gives a second order accuracy even in non-uniform logarithmic grid. Here, we compare our numerical scheme and with the analytical result to validate the scheme. We also show a comparison with the Chang-Cooper algorithm. We consider this Fokker-Planck equation with this initial condition and the following computational geometries. And as you can see from this plot, our result, which has been shown with the dotted line, matches very closely with the analytical result, which is shown in the solid line, in compare to the Chang-Cooper result, which is shown by the dashed line. Also, in the right-hand side plot, you can see the accuracy of our code, which is SSP, is of second order, whereas the Chang-Cooper gives a first order accuracy only. With this numerical code of energy evolution of non-thermal particle, we proceed to simulate the radial lobe of FR2Z. We consider a non-relativistic axisymmetric simulation to create these lobes. For dynamical simulation, we consider a non-magnetized ambient medium with a King's-like density profile and temperature of 2 keV. We then inject a light jet through the cylindrical nozzle with the jet parameter shown in this cartoon. For the emission modeling, we inject enough macroparticle to uniformly fill the entire jet cocoon. To evolve the energy distribution, we solve this equation with various losses and a phenomenologically motivated term or acceleration timescale to simulate this momentum diffusion and acceleration. This is the timescale that we have chosen. This timescale has the ability to mimic the turbulence decay process usually observed in various astrophysical scenarios. This tau c is the cooling timescale for each and every macroparticle from gamma max 10 to the power 5 to gamma min 1. And alpha is a parameter that we tune to get various acceleration scenario. We solve this equation with an initial condition of a very steep power law given by this. Here we show the density evolution of our simulated jet, and one can see a thin lobe kind of structure being formed at very early time, which through time expands transversely to give a radial lobe kind of structure at later time. Further, all our simulation or all our result would be pertain to this last time scale where the radial lobe could be seen to form. Here we show the effect of stochastic acceleration on single particle spectra for various case scenarios as shown in this table. We have considered 5 case scenarios, and these 2 plots depict the particle spectrum for 2 different macroparticles which got shocked at different times. For case A, one can see, as shown in this blue line, one can see a power law kind of spectrum with an exponential cutoff, which is typical for this kind of behavior, or for shock acceleration kind of behavior. For case D and E, where turbulence decay process has been turned off, one can see a ultra-relativistic Maxwellian kind of structure being formed for this macroparticle, where some transient feature for this macroparticle, which indicates that the particle spectrum is in process of getting into an ultra-relativistic Maxwellian. Interestingly, for case B and C, where the turbulent decay process has been taken into account, one cannot see a steady state kind of spectra for the particle spectrum, but one sees a cutoff which moves towards a lower energy. Now, after showing the effect of single particles, we show the effect of stochastic acceleration on collection of particles. Here we show the histogram of cutoff energy due to various cases as described in the previous slide. For case A, we can see a broken power law kind of structure for the cutoff energy histogram, and the break corresponds to the particle injection, as I have shown above. The break kind of depicts the particle injection with gamma max 10 to the power 5. It is a continuous process, that's why a break occurs here. Whereas for case B and C, where turbulence decay process has been taken into account along with STA, one can see some additional peaks is getting formed, due to the sustained acceleration that the STA provide to the non-thermal particles, one can also see some transient kind of peak, which are due to the macro particles are momentarily getting shock accelerated in the system. Here we show the synthetic spectral energy distribution of our simulated radio lobe, where one can see for stochastic acceleration, when stochastic acceleration is taken into account, some low energy, some low frequency peaks can be seen to occur here. Some peaks can be seen in the X-ray kind of regime as well, because of the transient feature that I have shown in the earlier slide. Interesting thing is to note that with stochastic acceleration, one can get a significant amount of X-ray emission due to ICCMB, which were not present in the case of only shock acceleration. These peaks are also a manifestation of the transient peak that I have shown above. So one thing is that all the peaks shown here have a direct correspondence to the peaks that I have shown in this slide. Further, we show the spectral index map of radio lobe for different cases. The spectral index distribution following the black line can be seen here, where one can see the spectral index gets a very minimal kind of value for the case of only shock acceleration, where the value gets increased when stochastic acceleration is induced, and the span of the constancy can be seen to get decreased with higher stochastic acceleration because of the turbulence decay process. And as I have shown in the motivation slide, this has been observed in various observations as well, that radio lobes kind of give a constant spectral index distribution, which can get modulated if we tune the stochastic acceleration. So by this, we come to the summary of our work. So we have extended the Lagrangian particle module by incorporating Fermi second order acceleration process with a second order accurate numerical algorithm. We then apply the numerical algorithm in order to compute the emission features from radio lobes of FR2 jets. Particle spectrum, as we have seen, shows various curvature due to the stochastic acceleration process, and the cutoff shifts toward the lower end due to turbulence damping, where without turbulence damping scenario, we got to see a particle spectrum which was steady in nature. Also, in the collective effect of STA, we can see various additional peaks in the cutoff energy distribution, which has a direct correspondence to the peaks observed in ACD. The ACD shows peaks in X-ray due to ICCMB, and which can only be occur due to which we can only get due to stochastic acceleration. Also, we have shown the spectral index map, which indicates a higher photon spectra or harder photon spectra in radio frequencies due to STA. That concludes my talk. Thank you. These are the references.
Thank you, Sharon. Questions from the lecture hall?
Sharon, very good work. Okay, extremely good work.
Thank you.
The particle injection that you are for this particle evolution,
okay,
of acceleration and all. So this particle injection that you are giving probably at the base of the jet or somewhere.
Yes.
But what is how you're guessing that number?
Okay. So
is there any physical argument in which you are fixing the normalization parameter as well as the power law? Or
Okay. So the thing is, the particles that we are injecting at jet base does not have anything to do with the particle spectra that I have shown here. Those particles are the Lagrangian particle that will going to flow along the fluid. But here we have taken the initial spectrum to be like this, as I have shown, and the chi-naught part, which is the normalization part, has been taken such that the particle stays in a sub-equipartition regime. So we calculated the magnetic field at the jet base, and considering that magnetic field, we have injected the macroparticles with a energy distribution which has a normalization due to the fact that particles are staying in the sub-equipartition regime, and then we let those macroparticle to flow with the fluid, and we see how the particles distribution gets changed due to this stochastic acceleration. So the injection of the macroparticles has nothing to do with this particle spectrum that I have shown here. The particle spectrum only gets governed by the normalization factor that we have shown here, and which tells you that the particle starts with a sub-equipartition energy. That's it.
No, it will not. I mean, whatever you inject will not have any effect there, because after all, you're solving a diffusion type equation, right? So that is I understood. Anyway, okay.
So the macroparticle injection is done means to uniformly fill the cocoon area or jet cocoon area, so that we can sample the whole jet cocoon area, and we can sample all the energy spectrals and all the differences in the energy spectra that the jet cocoon induces in the macroparticles.
Okay, fine.
Any other questions, both from online and people present in the lecture hall?
No, ma'am, there is no question.
Okay, if there are no more questions, let us thank Sayan for his talk. Please answer your screen now. The next talk in this session is by Shilpa Sarkar, and she will be speaking about funnel flows around strongly magnetized neutron stars. So I think one mic will have to be muted. There's a noise. Shilpa, can you speak?
Hello.
Are you using your laptop? Then just mute this LHC one, I think. Try speaking now. Shilpa, try to speak something.
Yeah, hello.
Okay. Try.
शिल्पा की इको शायद ज्यादा हो रहा है, आप लोग को
Hello, can you hear me?
Yeah, it's better now. Okay, so Shilpa, I'll give you a warning at around 10 minutes.
So, hello everyone, I am Shilpa, and today I'm going to talk about the accretion flows, which are also known as funnel flows around strongly magnetized neutron stars. So here you can see a neutron star, which is accreting matter from its binary counterpart. So the accreted matter has some angular momentum, because of which it first forms an accretion disk around the neutron star. After which, when the magnetic pressure of these field lines exceeds the ramp pressure of the matter, this matter is strictly channeled onto the magnetic field lines until it reaches the poles of the star. So basically, we are going to model this mainly to understand the underlying physics that is present in these systems. But modeling of these accretion flows is not trivial, and hence we took recourse to certain assumptions. The first assumption is that we consider the magnetic moment to be co-aligned with the rotation axis of the star. And the second thing is that we assume strong magnetic fields. So because of this strong magnetic fields, the matter, so there is no slippage between the matter and the magnetic field lines. And the second thing is that because of since these field lines are strongly anchored to the neutron star surface, these magnetic field lines as well as the matter, they co-rotate with the same angular velocity as that of the star. So zooming into this section a bit more, so the matter accreted from the accretion disk is basically subsonic in nature, but as the matter is accreted further because of gravity, this subsonic matter becomes supersonic after crossing a certain sonic point. And then this supersonic matter, because of the hard surface of the neutron star, it forms a shock, which is also called as the surface shock or the primary shock. So basically this forms because of the hard surface. And after this, the supersonic matter, it becomes subsonic, and all the kinetic energy of this matter is radiated into the form of different emission processes, after which it slowly settles down onto the surface of the neutron star, satisfying the neutron star boundary conditions, that is velocity is 0 at radius equals to the star surface. So most of the work that has been done till now, they considered only this particular funnel, mainly because more than 95% of the emission comes from this region. But as I will show you that there are distinct spectral signatures from this pre-shock region as well. So there is a necessity to study the full solution that is connecting the accretion disk to the poles of the star. So apart from that, in order to obtain the spectrum, we need to work in the two temperature regime. So what makes a flow to be of two temperature? So mainly because there are different masses of, because protons and electrons, they have different masses, and hence they will be prone to different emission mechanisms. The second thing is that the infall timescales are shorter than the Coulomb coupling timescale. So Coulomb coupling timescale is the timescale in which the electrons and protons, they interact with each other and settle down into a single temperature distribution. So before that interaction timescale, if the matter falls to the central object, then the electrons and protons, they will be thermally decoupled and they will possess two different temperatures. And since the third point is that the electrons are the main radiators, because bremsstrahlung, synchrotron and everything, they mainly means electrons are more prone to this radiative mechanisms, the temperature of the electron is bound to be different from the protons. So we expect a two temperature flow in the system. So these types of flows are generic in nature, and since we have information of the electron temperature, it helps in computing the spectrum. So these types of flows are more realistic in nature. Now there is a serious problem that exists in two temperature flows. So one temperature flow is when the electron and proton have a single temperature distribution. So when we come to the two temperature regime, the number of equations doesn't change, but there is an additional variable, which is the temperature. So this says that the system is degenerate because we do not have any principle which may constrain the relation between the two temperatures, or no extra equation is there which may constrain the temperature. So this problem is indeed serious, because a lot of work have quoted these things, that there is a degeneracy problem starting from 1980, and it is still the people tell that yes, there is a degeneracy. So how this degeneracy was removed in earlier works is that either they parameterize the proton and electron temperature to certain ratios, or they have forced some relation between them. That is, they have insisted some equation that like the heating of the electrons is equal to the cooling of the electrons. So this made an additional equation because of which they could obtain the temperature. But this, so this degeneracy is irrespective of the nature of the central object, and it is intrinsic of two temperature regime. But this thing is not means that this solving, like parameterizing these things, is not consistent. So in a recent simulation done by these people for accretion flows around black holes, you can see that they parameterize the ion and electron temperature to different values, and we can see that the topology of the system actually changes, actually differs if we take different kinds of arbitrary parameterizations. Even when they plotted the efficiency with respect to the accretion rate, we can see, suppose for the 10 to the minus 2 Eddington rate, we can see with the different values of ratios, the efficiency of the system changes. But this should not be the case. System should not be degenerate. For a given constant of motion, there should be a given solution. So there is a need to find a general consistent methodology. So coming back to the neutron star case, so this is what we call the Mach number versus radius plot. So this is a neutron star accretion solution where the matter starts from subsonic values, crosses the sonic point, becomes supersonic, and because of the hard surface, as I've said, it undergoes a strong shock near the surface. And this is the corresponding spectrum obtained from the different radiative processes like bremsstrahlung, synchrotron, and their comptonizations. So these are the set of constants of motion. But for the same set of constants of motion, we can see that there are different solutions where few solutions passes through the outer sonic point, few through the inner sonic point, and few even harbors a shock. And correspondingly, the spectrum also changes. So what we did is we found an entropy accretion rate formula, which is given like this. So we have validated this entropy accretion rate formula in case of black holes earlier. But the catch is that this entropy, since the system is dissipative, so this entropy accretion rate form can be only obtained, the entropy measure mainly can only be obtained at a point where the gravity overpowers any other interaction. So the interaction timescales are very much larger than the infall timescales. So in case of black hole, it was very easy and it was the event horizon when we could measure the entropy. But in case of neutron star, this is not the case, because at the surface of the neutron star, the velocity is actually zero and not the velocities are higher, where the infall timescales would be larger. So what we did is that we integrated the supersonic branch of solution further inwards until we reach a point Rm, say, where these conditions we see is satisfied, and hence we measure the entropy of this Rn point. So this solution is actually an extension of the original supersonic branch of solution, and we call it as the ghost solution. So this solution physically, it means that just outside the star surface, this flow doesn't know whether there is a neutron star here or not. So this solution is actually a part of the supersonic branch. Hence, we measure the entropy of this point Rn. And after measuring the entropy of all the degenerate solutions, we find that the entropy maximizes at a certain solution, and following the second law of thermodynamics, that nature prefers a solution with maximum entropy, we select that solution. So in the earlier set of constants of motion, so this is the maximum entropy solution where the solution passes through the outer sonic point, and this is the corresponding spectrum. Now, this is a typical accretion solution and its spectrum, and these are the constants of motion for it. So this is the velocity plot. So the velocity, as we can see, near the neutron star surface, there is a jump to lower velocities, after which, when it nears the neutron star surface, the velocity decreases, and finally it settles down onto the neutron star surface, while the number density increases as the matter is getting accumulated on the surface. And this is a magnetic field, and this is the conserved Bernoulli parameter, and these are the two different temperatures. So this is the proton temperature, this solid line, and the dotted one is the electron temperature. So we can see that the electron temperatures, because it is more prone to radiation mechanisms, the temperatures are less, but when it reaches the neutron star surface, the temperatures of both the protons and electrons, they decrease, and they settle down onto some constant values. And this is the adiabatic index for both protons and electrons. So adiabatic indexes is 4/3 when the system is relativistic, while it is 5/3 when it is non-relativistic. So the relativistic means that the thermal energy of the matter is greater than the rest mass energy of the system. And non-relativistic is when it is less. So not only the temperature, but also the mass of the species is important. So since we are dealing with two different species, we actually used a relativistic equation of state for multi-species flow. And we can see that the protons and electrons, they are almost non-relativistic, very far away, while as the matter is accreted, the protons remain mildly non-relativistic, but the electrons become relativistic. So there is a need to study these flows using a relativistic equation of state. So coming to the contribution of different regions to the total spectrum.
Shilpa, you have 2 more minutes.
Yeah. So what we do is divide different regions and plot the corresponding spectrum. And as has been earlier discussed or concluded by most of the authors, we also found that 99.98% luminosity comes from a region very close, that is 2.418 to 2.829. But as I had said earlier, that there are signatures, spectral signatures of this pre-shock region. So these are the constant of motions which has a secondary shock as well, apart from that primary shock. So if this solution didn't have this secondary shock and the solution only passed through the outer sonic point and had a primary shock, so these are the two spectrum which we get, and we can see that there is an extended power law tail when in the pre-shock region we have a secondary shock. So this tells us that there is a need to study the full transonic solution, full accreting solution, which connects the accretion disk to the neutron star poles. So to conclude, there is a need to work in the two temperature regime in order to obtain the spectrum, and there is a degeneracy problem which we need to attend and get correct information of the system. And we have done that, and we didn't study only the funnel, we actually studied the full global solution and full accreting solution, which is actually needed to get a bigger picture of the system. So thank you.
Thank you, Shilpa. Questions from the audience?
This work. Anyway, I was just wondering about two. One is that this is 1D, right?
Yeah.
So we know that cooling flows. This is basically you have cooling.
Yeah.
So cooling flows sometimes are stable in radial perturbations, but if you inject non-radial perturbations, for example, azimuthal or meridional, then it becomes unstable. So will it really hold if you do multi-D, like more than 1D? And second is that.
But these are steady state solutions. So.
Yeah, so even if you do stability analysis of the steady state solution, if you perturb it, then it might be.
Actually,
be like
I have done the stability analysis of these solutions, and I found that in context of the entropy thing, because there was many degenerate solutions. So for that, I studied the stability of the maximum entropy solution, and I found that all the solutions are stable, but the most stable one was the highest entropy solution. Yeah, so the stability analysis was
that
done.
We know from the earlier things like nature prefers the maximum. And second was that generally earlier works, what you mentioned rightly, that they have only considered the post-shock region, which has been modeled as a plane parallel atmosphere.
Yeah.
But you are considering the pre-shock region as well. Then probably a curvature term will add. So how are you tackling it? Because it's not really plane parallel atmosphere. It's curving in.
Yeah,
it's following a curving path.
Yeah, yes.
It's falling onto the neutron star.
So since we are assuming the strong field assumption, so actually the magnetic field decides the geometry. So that reduces one equation. So there is only a r theta connection, which gives us the total 1D flow. Means that 2D or the curvature term you are talking about, that reduces to a 1D nature.
Okay, Bhargav has a question.
Yeah, hi Shilpa, can you hear me?
Yeah.
Hi, very nice and an interesting talk. Actually, you rightly mentioned that usually people parameterize the ratio of proton to electron temperature. However, in your steady state calculations, since you basically start from the outer boundary by injecting some parameters and you basically go inside. And since you have two temperatures, T and TB, you must need to impose certain boundary conditions at the inner point. So how critical are those boundary conditions? Because does those boundary conditions govern your formation of secondary shocks? And what, in the first question is, what do you put for those boundary conditions? And whether they govern your formation of secondary shocks, inner boundary for TE and TP.
Okay, so actually in the inner boundary only, we start from the inner boundary itself. So from here we start.
I cannot see your screen.
Okay. You can see.
Now I can see, yes.
Yeah.
Hello, Shilpa.
Yeah, actually there is a problem here. Bhargav, can we discuss it later?
Yeah, I think it's better we discuss it later. Yeah, thank you.
Okay, are there any other questions for Shilpa? Okay, if there are no more questions, let us thank Shilpa and invite the next speaker of this session. The next speaker is Zahoor Malik. So, is he giving the talk in person?
Yes.
Okay. So Zahoor will be talking about model independent redshift estimation of BL Lac objects through very high energy observations.
Good afternoon, everyone. Myself is Zahoor Malik from University of Kashmir, and I am doing my work with in collaboration with Dr. Sundar Sayan from Baba Atomic Research Center, Mumbai. I can see the tiredness on the face of all the participants because of the compact schedule. So I will try to not make you feel bored for next 15 minutes. So please bear with me. So just have a look at the title. I'm going to explain it in the next slide. You have heard about these active electric nuclei from previous some days. So I'm not going to detail. There are this subclass of radio loud active electric nuclei, which we call as blazars. So blazars are the objects having jets pointing towards our line of sight. And these blazars are further divided into FSRQs and BL Lac objects based on the strength of the emission and absorption lines. In case of FSRQs, they are having strong emission absorption lines, and in case of BL Lac objects, they are having this emission or absorption lines are absent. You can see from the left top that there is a BL Lac object given, and you can see the spectrum. It is a featureless continuum spectrum. The absorption or emission lines are, as compared to other objects, they are not there. So like this feature we use to calculate the redshift, like the distance estimation of these objects. So if the emission or absorption lines are not there, so you will not be able to, it is very difficult. So this is the main problem I have addressed in this work. And how we are doing it is, since this redshift is a spectroscopic parameter, so here we are using VHE astronomy. That is a totally independent, different approach we are using for from spectroscopy. What we are doing is, you can see that consider that. Can you see my pointer? So if you, this is a BL Lac galaxy, and jet is pointing towards us, and this dark blue patch, it's a diffuse emission radiation in the universe. Particularly here, it is the extragalactic background light, the second dominant diffuse radiation after the cosmic microwave background. So these BL Lac galaxies, they are sources of VHE photons in the universe. So what happens is this: the photons, the VHE photons, comes from this BL Lac galaxy, and they interact and root with this extragalactic background light photons, and pair production occurs. So the spectrum will change. For example, here it is the source spectrum. It will be without attenuation from extragalactic background light. And what we are collecting here is the observed spectrum, which will be after the attenuation. So the spectrum, for example, if it is having some slope here, the index here, it will steepen up because of the attenuation. Here you can see it will steepen up because some of the photons will be attenuated. Okay, and this feature we are using to calculate the redshift. How I'm going to present in next slide. So there are two problems here. First problem is that we don't know the intrinsic spectrum. This intrinsic spectrum we don't know, and other thing is we don't know accurately this amount of EBL which is present, because the direct estimation of EBL is hindered by the foreground emission from our own galaxy. So since I told you that this is hindered by the foreground emission of our own galaxy, so we are going to the cosmological models, EBL cosmological models. You can see these lines. These are different cosmological models which are giving us the EBL, amount of EBL which is present in the universe. And in this work, like I am addressing this, like also how valid they are. So these EBL models are based on some approximations and assumptions. I am checking that also in this work. So the study starts from here. We have taken all the sources which are detected at VHE, okay, and which are having certain redshifts. And I am checking a correlation with the index, spectral index. I told you before that spectral index will be steepening. So spectral index information I am taking from VHE, from these papers I am taking from literature, and I am checking the correlation for all the sources. The first plot on the left side, you can see this is for pure HPLs, energy peak replacers, and you can see that there is a nice correlation. Although error bars are very high, but you can see that there is a nice correlation. And see, for the sources which are at higher redshifts, the indexes are higher. That means the spectrum is steeper. Okay, and for EHBLs, extreme EHBLs also, you can see that there's a nice correlation here. And these are some correlation parameters. You can see for both, we are getting a nice correlation, and where we have fitted a function to get the signature. So this signature we are telling it is because of the extragalactic background light on it. Okay, to cross check this, what we are doing is we are checking it like for the other wavebands, because we want to see is this because of the evolution of the universe. It can be due to the like intrinsic spectrum can be related to redshift. For that case, we are checking with lower wavebands, and we are checking for X-ray and low energy gamma rays. Here we have used 4 catalogs, X-ray catalogs, and one of 4 FGL catalog for low energy gamma rays. We see that there is no correlation at all, and you can see from the plot also that correlation is not there. So that further asserts us that the correlation in VHE is because of the extragalactic background light, and the function we fitted here. This function is a simple approach, but see, like this can be used without any. You can use it anywhere if you know the index, if you know the spectral index, and using this function, you can get the redshift at any index for these sources. Okay, so using this best fit function, we have calculated the redshift of 6 of the sources which are there, and they are having some previous estimates also, some spectroscopic estimates like upper limits and all. See, you can see here that in spite our approach is totally different, but still our estimates are matching with the previous estimates. Okay. I want to add here that I told before also that this is the spectroscopic parameter. Redshift is a spectroscopic parameter. We are calculating it using the VHE astronomy, and still our estimates are matching with them. You can see these are the previous works. And the other part of the work is I am checking the validity of the EBL models. We know that the observed spectrum is given by flux is given by the intrinsic, and this is the e raised power minus tau factor is from the opacity due to EBL. And here we consider the intrinsic flux is a power law, because this is an observational feature only. So we have seen that most of the sources are having this power law behavior in VHE, and we are considering intrinsic flux as power law also. And then we reach here that observed index will be given by the intrinsic, and this is the d tau by d Lani factor, which is the opacity factor. So I told you before also that we don't know the intrinsic spectrum, and this d tau by d Lani we are using from cosmological models. For this first term, gamma intrinsic, what we are doing is we are extrapolating that best fit line to z equal to 0, redshift is 0. And why redshift 0, you will see that the distance will be minimum, and we are going to the source to measure. Okay, that forms the intrinsic index. This is the assumption we are extrapolating, we are using as an assumption. And that intrinsic we are getting from their index, and the tau values we are taking from different cosmological models, and we are comparing with the observations. Here you can see that this black line is the best fit line, and these different colored lines, they are which are in legends also, you can see these are some different cosmological models. You can see up to 0.3 redshifts in both the for HPLs and HPLs. You can see that models fall within these error paths, and to check the behavior of these EBL models at higher redshifts, what we have done is we have taken FSRQs. There are only 7 FSRQs detected in VHE, and I am going to talk about that also. So you can see that these, although number of sources are very less, but you can see that these models deviate quite significantly. So here at higher redshifts, what are we doing is we are calculating this deviation. We are adding a correction factor to the EBL, existing EBL model, so that the model line here, the model line, it comes to the observational line. We are including this redshift dependent, this correction factor here, and we are updating that EBL model, existing EBL model. We have used a recent EBL model, and this is the last thing I'm going to talk about is that this EBL, since all these, what our work is saying is the EBL is less as compared to what we are estimating using these EBL models. You can see this from this line, the EBL is more using this model, and our model says it is very less. Because of this EBL, like high EBL, what these models say that we cannot see the sources beyond some redshifts in VHE. That makes the cosmic horizon, and that I am explaining here. Before it was 0.1, redshift was 0.1, that they were saying we cannot see after 0.1. Nowadays it is updated because of some recent instruments in VHE, but it is settled. But we have found the FSRQs which are detected at like 0.9 redshifts. That itself talks about these models, how they fail at higher redshifts. Okay, so we have updated and we have taken care of the correction using observations, and we are using that updated EBL, and we are seeing for FSRQs, which we have taken all the FSRQs which are detected till from the Fermi catalog. We have found that there are 744 FSRQs which are detected at Fermi, and what we are doing is we first should know the intrinsic index. We are making an assumption. We are extrapolating the intrinsic spectrum from the Fermi towards VHE. And then, since this is the intrinsic index, we have to make the EBL correction. And we are making the EBL correction using our updated EBL model as well as the original EBL model. You can see here clearly that this black line is our EBL model, which is saying that EBL is less as compared to the original model here. And then we are overplotting the different sensitivities of different telescopes. We are actually checking for the possible detection of these sources, because these IHCTs are pointing telescopes. you have to be sure like which source can be detected. So you don't know, you have to point that telescope towards that source. So after plotting the sensitivity curves of different telescopes, you can see these sources at redshift 0.7. Okay, and the original EVL model, this green dotted line says this cannot be detected, but our EVL model is saying that this can be detected by the upcoming CTA. And we have checked these results with the existing 9 FSRQs which have been detected, and we have seen our results are favoring all the 7 that they can be detected by the telescopes. That was the cross-check of our work. And among 744, we have
2 more minutes now.
Yeah, I will complete in a minute only. So among 744 FSRQs, we have seen that there are 37 FSRQs that can be detected by upcoming Chernobyl telescope array. And since considering the blazars are very, like they are very variable objects, so sometimes the flux becomes 10 times also. So we are considering here an situation where the flux doubles, it becomes 2 times. And in that case, we found that there are 44 additional sources which can be detected by CTA. And here we are preparing the catalog for the CTA and other instruments. Interestingly, we have found that some of the sources can be found by the existing IACTs, and we are publishing this work so that we can cross-check that. And to summarize, we have we have used a novel approach to estimate the redshift of objects. Alternative that is a quite good alternative to use. And we have made a catalog for FSR that can be detected at VHE using IACTs. Thank you so much.
Thank you, Zahoor. Any questions for his talk?
Hi. So you develop your own EVL model and you try that model with FSRQ. But in case of BL Lac sources, I think high frequency BL Lac sources you have used, but you didn't try that model with HBM sources?
Yeah, you can see here, I was saying that the existing EVL models, they are below, like for BL Lacs, you have seen that FSRQs are mostly detected at higher redshifts. Like, I don't know the exact reason, but it is there. It may be because of the evolution or Malpass bias. But you can see before 0.3 redshift that these models are behaving well. They are falling within the error bars, and they are falling within that, slightly within that error band, 1 sigma error band. That's why, but here you can see they're deviating much. So that's why we tried with FSRQs.
Have you tried with BL Lac, like this new model?
Yes, we have tried the new model in BL Lacs also, and we found, I have not included that slide.
Yes,
I should have included.
That's why I'm asking, because you didn't.
Yeah, and that ABL model is falling well inside that 1 sigma error band.
So it is falling if you.
Yes, since the ABL model is, we have done that using observations only, so it is mandatory that it should fall.
It's better, it's like both for SBL and FSRQ, both it's applicable for both.
Yes,
Yeah,
yes.
good. Cool. Thank you.
There's one question from Pankaj.
Nice work, Zahoor. So I just want to ask one thing is there was some issue with the EBL estimates even that are existing right now, because of which people propose that this astroparticle physics people propose the axion-like particles. Now basically we expect EBL, but we were getting lesser attenuation. So how does this model, I mean, you are saying that, okay, you can detect sources up to higher redshift, right? Compared to the what the existing model is.
Yes.
So how does this goes with that, those proposed axion-like particles scenarios?
See,
because they also propose less EBL, like the way your model, I think, is predicting less EBL compared to what it is.
Okay. See, here this EBL model, we are developing it from observations only. Okay. Frankly, I will say I don't know much about Axion, what you are talking about, but this is totally based on observations. And after cross-checking, we are finding that this EBL model for the existing like FSRQs, we have checked this, and this EBL model works well, and it is showing that EBL is less only.
Yeah. Okay. I mean, that was also the claim actually. What observationally, I mean, earlier this was exactly the reason that EBL is less compared to what is predicted or what is expected, and that's why the proposal for this new particle was there. But okay, yeah. Thank you.
Okay. Thank you.
Okay, thank you, Zahoor. Let us move on to the next talk, which is the last talk of this session. And the last talk will be given by Brajesh. He will be speaking about the Type 1b supernova SN 2017 IRO, a moderately luminous event with a possible binary progenitor. So Brajesh, you may please share your screen.
It is fine. Am I audible?
Yeah, a little louder, please.
Hello.
Yeah, Brajesh, you can start.
Okay. Thanks. So, hello everyone. Good afternoon. So this is since this is the last talk of the session, so I will try to finish my presentation timely. So this is the title of my presentation, and this work has been done with in collaboration with Avinash Singh, DK Sahu, and GC Anupma. So before I go further, let me briefly introduce you about the core collapse supernovae and their progenitors. So just wait. Okay. So core collapse supernovae are the gravitational collapse of the iron core of massive stars greater than 8 solar masses during the end stage of their lives. And these are broadly classified into two groups based on their observational features. So type 2 with spectra, their hydrogen in their spectra, and type 1 without hydrogen in the spectra. So in the left side of here, this figure, you can see that the light curves have diversity, and in the right panel, the spectral classifications are presented. So you can see that in type 2 events, hydrogen is very strongly present, and in type 1 events, hydrogen is absent, but there could be a presence of helium features, mainly in type 1b, type 1b, and type 2b. And there is another class, type 1c and broadline type 1c, where both hydrogen and helium features are absent, but strong features of silicon is present. So actually the type 2b, type 1b, type 1c, and type 1c broadline core collapse supernovae are also known as strip envelope supernovae, because their progenitors strip off the outer envelope before the explosion. And it is believed that there are two progenitor channels of strip envelope supernovae. So first is the progenitor with evolved single massive star greater than 25 solar masses, ultra stars, and these are losing their outer envelope by strong stellar wind. And the second channel is possibly with smaller progenitor masses less than 20 solar mass in a closed binary system, losing its outer envelope to the companion by the accretion. And it is interesting to note that direct detection of stripped envelope progenitor candidates have been possible only for a few cases. For example, supernova 1993J, 2011 DH, and 2016 GKG. However, direct detection of type 1 BC progenitors have not been successful till the date, but upper limits have been provided. For example, in IPTF 13 BVN and 2017 EIN and 2019 YVR. So stripped envelope supernovae are generally characterized by bell-shaped structure, which is mainly powered by thermal energy released as consequence of nickel to cobalt and iron decay. And the observational properties of steep envelope supernovae as diverse, and their nickel masses have range of 0.1 to 0.4 solar mass, and the ejecta mass is 1 to 6. And similarly, the explosion energy and also the absolute magnitude has a wide range, minus 16 to minus 18 magnitude. So overall, the early and late phase light curve evolution and spectral properties can be used to estimate the observational parameters, and consequently we can constrain the progenitor masses. So considering an opportunity of a nearby supernova type 1b, we investigated its observational properties in detail. And this object was discovered on 30th of November 2017 in NGC 5480, and we started its follow-up from 1st of December. And UVRI optical imaging and spectroscopy was obtained with 2-meter Himalayan Chandra telescope with H-FAS instrument, and the total span was around 277 days. And we obtained around 40 and 35 epoch of imaging and spectroscopy. In the right panel, this is showing the location of the supernova 2017 IRO, and another event which was also occurred in the same galaxy, supernova 1998L. So this is the light curve evolution. In the left panel, you can see the evolution of apparent magnitude, and in the right panel, we have compared the p-band magnitude with other similar type of events which have study starting from early phase to the late phase. So this is in this table, I am presenting the various parameters like delta M15, which is parameter the decay of magnitude from the maximum within 15 days, and also delta M40 parameters. So in the right panel, in this legend, you can see that the evolution, early evolution of 17 IRO is in between the fast evolving some of the events like 2007Y, IPTF 13 BVN, and slow declining event like supernova 2009 JF. So this this is a kind of indication that ejecta mass of 2017 IRO is intermediate between these slow and fast declining events. And here I am comparing the late phases. So the steep envelope supernovae, they are declining faster than the expected decay rate, that is around 1 magnitude per 100 rate. So the lower opacity, this is indicating the lower opacity of ejecta for gamma rays, or we can also say the incomplete trapping. In case of 2017 RO, the VRI band decay rates are around 1.8, 1.5 and 1.9 magnitude per 100 days. So if you see very carefully this phase, especially after around 150 days, there seems that there are two groups of events. So one is fast declining, so fast declining, and another is slow declining events. So in slow declining events, there are two supernovae, 2012 AU and 1999 DN. So possibly there is additional powering source, maybe interaction of ejecta with the CSM and also the magnetar. However, there are another group which is fast declining group, and supernova 2017 IRO is coming in this group, including 9JF and 2007Y and IPTF 13 BVN. This could be possibly because of incomplete trapping of the gamma rays in the supernova ejecta. So here is the quasi-bolometric light curve. So it is constructed using UV high magnitude. And to construct the bolometric light curve for supernova 2017 IRO, we have used total extension of 0.28 magnitude and distance of around 31 megaparsec. And the left panel is showing the bolometric, quasi-bolometric light curve and compared with similar type I events. And you can see that for 2017 RO, it is in intermediate between the 2012 AU and other events. And the right side is the temperature and radius black body fit. And here is the spectral evolution. And the left panel is the pre-maximum to early post-maximum phase. And you can clearly see that various lines of helium are appearing and indicating that this is type 1B event. And also in the bluer side, there are calcium-2 JHK features, and also the RN features are appearing. And in the right panel, you can see that various features of instantium-2 and RN2 are starting appearing here. This is a late post-maximum spectral evolution. Beyond 60 days, you can see that the forbidden lines arising due to oxygen 6300, 6364, and other calcium lines are started appearing. And the nebular line 5577 extam is also visible with oxygen 17774. This is nebular phase spectrum, and it can be seen that spectra are mainly dominated by forbidden emission lines of oxygen 1 and calcium 2. And also in the right panel, the semi-forbidden magnesium line is there, but it is very weak in comparison to other similar type of events. And this is the plot of line velocities, and different line velocities are estimated here and plotted. And the helium-1 5876 features, that is around, it reached around 11,000 and then declined to around 9,000 kilometers per second. And then it can be also seen that the line velocities of helium-1 is of 17 IRO is very much similar to 13 BVN. We estimated the physical parameters of the explosion using the semi-analytical formulations of various authors. And the plot here is showing this is showing the Winko fit model, and there are 3 additional curves which belongs to nitrogen 1994 energy production curves. And it can be seen that the best model which is here is 0.1 solar mass for the nickel mass. So using these formulations, we estimated nickel mass in the range of 0.05 to 0.1, and ejecta mass 1.4 to 4.3, and the kinetic energy 0.8 to 1.9, 10 to the power 51 Earths. Here I will discuss about the nature of the progenitor star. So basically, the oxygen 1 6300 6364 line flux in the nebular spectra of strict nebular supernova can be used to estimate the neutral oxygen mass that is required to produce the emission. And using Umoto 1986 relation, this relation, we can estimate the oxygen mass, where MO is the mass of the oxygen, and D the distance, and F is the flux of oxygen line, and T4 is the temperature that is for the emitting region, which is in the units of 10 to the power 4 Kelvin. So for 2017 IRO, we have used a distance of 30.8 megaparsec and oxygen line flux of 2009 day. It's this value, and T4 we used 0.4. And note that we have used this as assuming as a lower limit of the temperature for oxygen emitting region, that is 3400 Kelvin. And in this way, we estimated oxygen mass of 0.35 for this object, which is for a progenitor mass range of 13 to 15 solar mass. And it should be also noted that we can use oxygen to calcium, the oxygen 1 to calcium 2 ratio to constrain the progenitor mass. And for our object 2017 RO, this is around 0.1, sorry, it is around 1, which again support that this estimated mass range for 17 IRO is towards the lower limit. And now again, nature of the progenitor star, we have plotted the flux ratio of various type 2, type 1 BC supernovae in the left panel. And it can be seen that generally type 2 events have lower flux ratio. And there is considerable dispersion in steeped enveloped supernovae. So it again indicating that there is possibly there are two different populations of 1 BC and consequently their progenitors. So with all this, this is the summary of my presentation. The bolometric luminosity of 2017 IRO is around 42.4 up, indicating that this is a moderately luminous event, and the explosion parameters are in this range. The late phase light curves decay with moderate steepness, indicating incomplete gamma ray trapping by the supernova ejecta, and possibly there are two group of events, fast and slow decliners. And a neutral oxygen was estimated around 0.35 solar mass, and using the lower line ratio of oxygen 1 to calcium 2 and the neutral oxygen mass, we constrained that supernova 2017 IRO had a main sequence mass of around 13 to 15 solar mass, likely in a binary system, which is very similar to supernova IPTF 13 BVN. So thank you from my side.
Thank you, Brajesh. Questions from the audience in the lecture room? Any questions from the online participants?
Hello. Can you hear me?
Yeah.
Hi, Brajesh. This is Arvind here. Nice.
Hello.
So I was asking, like, if you compared the light curves of bolometric light curves with various supernovae, and you said that the decline is similar to IPTF 13 BVN.
Yes.
My question is, like, IPTF 13 BVN has some sort of detection of progenitor.
Yes.
So is there anything like that for IRO or something like that?
Actually, we searched the archival image of HST, but we did not find, the progenitor in case of 17 IRO.
So in that case, what is the limit? Like any limit you put to the luminosity or something like that?
No, actually, that particular region is very, that is in H2 region, and it's not easy to distinguish the, the particular progenitor luminosity or something like that. I mean, it's a very compact region.
Okay, thanks.
Okay, I think there are no other questions. So let us thank Brajesh for this very nice talk, and also all the other speakers of this session. Thank you all once again. The next session will start at 2:15.